Okay, let's carry this forward with another example of perhaps a more complicated chemical equation than the ones we've seen previously. Now, on its surface, it will look fairly similar. We've got some molecule reacting with oxygen to form CO2 and water. But it's a little bit more complicated than the previous examples, and we'll find a couple sub-rules that may help us with tackling these problems. So first, we approach it just the way we've approached all of the previous examples, where we list the elements on both sides so we know where we're starting. So here we've got 5 carbons on the left, only 1 carbon on the right in CO2. We have 10 hydrogens from this first molecule, only 2 on the right in water, and then we have 4 oxygens on the left and 3 oxygens on the right. Now the second step is to start by choosing the element that appears in the least number of formulas on each side. Again, we could start with carbon or hydrogen in this case because they both appear only in 1 formula on each side of the reaction arrow. But we'll start with carbon as we've done previously. So we balance carbon. We have 5 on the left. I simply need to add a coefficient of 5 on the right to get to now a case where if I relist my elements on both sides, I will see that I have balanced carbon. And there's been some slight adjustment, so nothing's happened to hydrogen, but on the right side I now have 11 oxygens because I gained several oxygens by adding the coefficient in front of CO2. Now the carbon is balanced, I'll move on to hydrogen. I have 10 on the left, 2 on the right. They only appear in 1 formula on each side, so I can simply add a coefficient in front of the water in order to balance hydrogen. And now I'm left with a case where I have 5 carbons on both sides, 10 hydrogens on both sides, so those 2 elements are balanced. And the only element that remains is oxygen. So we only have 1 oxygen, we only have 1 element left to balance. And oxygen, you will notice, appears in every single one of the formulas of our problem. There are currently 15 on the product side and 4 on the reactant side. So the last step then is to balance oxygen. But here we come to here's where it gets slightly complicated. We can ask, how exactly do we go about balancing oxygen? As I noted, it appears in every single one of the formulas. So which coefficient do I change? And this brings us to our 2 sub-rules that may be very helpful when solving problems like this. And the first of those 2 sub-rules states that once you have changed the coefficient of a formula in order to balance one element, do not change that coefficient again unless you change all of the coefficients at once. Now, what exactly do I mean by that? When would we change all of the coefficients at once? We'll get to that in a moment. But the first part of this, once we've changed the coefficient of a formula to balance one, don't change that coefficient again. What I mean by that is if we look at this equation, we can see that for CO2, we already changed that coefficient in order to balance carbon. So we don't want to change that coefficient again, since that would unbalance carbon. We would only change that again if we changed all of the coefficients at once, which I'll explain later. Again, the coefficient in front of water, we changed that in order to balance hydrogen. So we're not allowed to change these two coefficients when we're trying to balance oxygen. So then what I'm left with is the coefficients in front of oxygen, the diatomic molecule, and then in front of this C5H10O2. I haven't changed either of those 2, so I could potentially change one of those 2 coefficients. That sort of leads us to our second sub-rule, which is that fractional coefficients may be used during the balancing process, as long as you end up removing that fraction at the end by multiplying all of the coefficients by the denominator. And this would be the case where we change all of the coefficients at once if we multiply them all by the denominator of whatever fraction we use. Now, why would we use a fractional coefficient? Why would I write 1/2 or 5/2 or 1/3 in front of a molecule? We don't use 1/3 or 1/2 of a molecule. It's true we don't, but sometimes we want to do fractional coefficients simply to help us balance the number of atoms on both sides, and then we'll get rid of that fraction later. And the current example here for this equation is a case where a fractional coefficient would be helpful. We've already determined that we can't change the coefficient in front of CO2, and we can't change the coefficient in front of water. That leaves us only the coefficients in front of C5H10O2 and in front of O2 to potentially change. Now, when we changed the coefficient in front of CO2, we did it in order to balance carbon with the number of carbons in C5H10O2. And the same for the 5 in front of water. We did that to balance the number of hydrogens with the number that are currently in this molecule. So we don't want to change the coefficient in front of C5H10O2. We only want to change the coefficient in front of O2. Now, if we look at the total number of oxygens, on the left side we have 4, 2 from C5H10O2 and 2 from oxygen, O2. On the right side, we have 15 oxygens, and we note that that's an odd number. We have 5 from water and 10 from CO2. Because I have an odd number on the right side, and because I want to change only the coefficient in front of O2, it doesn't matter what whole number coefficient I put in front of it, I will never get to an odd number of oxygens. And so in order to get to an odd number of oxygens, what I'll use is a fractional coefficient. So I want to get to 15 total on the reactant side in order to match the 15 that are on the product side. I already have 2 from the C5H10O2, so what I need is 13 more. So if I place a fractional coefficient in front of O2, I can put 13 halves in front of O2. That will now get me 13 oxygen atoms, because remember the total number of atoms is the coefficient times the subscript. If the subscript is 2 and we multiply by 13 halves, I'll come out with 13 oxygen atoms, and then add that to the 2 from the C5H10O2, and that will get me to the 15 that I need. Now I can write out my elements listed on both the reactants and the product side, and we'll note that carbon is balanced, hydrogen is balanced, and oxygen is now balanced. However, we're not done, because as we said, we don't use an actual fraction of a molecule. So we can't have a fractional coefficient at the very end. We need to remove that fraction. We use it only to help us in the balancing process. And so this is where that last part comes in. We remove that fraction by multiplying all of the coefficients by whatever the denominator is. The denominator of that fraction is 2, so we multiply all of the coefficients by 2, just like we would for a mathematical equation. And that will remove the fraction, and we will be left with only whole numbers. So if I multiply everything by 2, I come out with 2 C5H10O2 plus 13 O2 gives us 10 CO2 and 10 water. And now we still note that all of my elements are balanced and my final chemical equation is balanced. Another example that may be a little bit more complicated. This is one involving ionic compounds and parentheses around polyatomic ions. And we just have to note how coefficients work, how subscripts work in these cases. Coefficients behave exactly the same. Subscripts outside of a parentheses means that every atom inside the parentheses is multiplied by the subscript that is outside. So in this case, for zinc hydroxide, there would be 2 oxygen atoms total, 2 hydrogen atoms total from this compound. Over here, there would be 2 nitrogen atoms, and there would be actually 6 oxygen atoms. Since there's already 3 oxygen atoms inside the parentheses, this 3 indicates specifically just that there are 3 oxygen atoms. But then the 2 means that there are 2 NO3 ions, and so there would be a total of 6 oxygen atoms present from this compound. We treat this pretty much exactly the same as we would in any of the previous examples. We just have to be aware that it looks a little bit different because of the parentheses that are present in some ionic compounds. So first we list the elements on both sides of the equation. This gives us now, we have 4 elements present rather than just the 3 that we've been doing before. We have zinc, oxygen, hydrogen, and nitrogen. We notice the zinc is already balanced, so we don't need to balance that one. And then we would look for the element that appears in the least number of formulas. Zinc only appears in 2, but as we noticed, it's already balanced. Oxygen appears in every single formula, so we don't want to start with that one. Hydrogen appears in 3 formulas, the zinc hydroxide, the nitric acid, and water. So we don't want to choose that one yet because nitrogen appears only in 2 formulas. That's the one we would like to choose. So we'll start by balancing nitrogen. We can do this by simply adding a coefficient of 2 in front of the nitric acid, and that will now give me a balanced case for nitrogen. So my zinc is balanced, my nitrogens are balanced, and it's only hydrogen and oxygen that are unbalanced. Since hydrogen appears in 3 formulas, but oxygen appears in all of them, we'll move to balance hydrogen next. And if I look here, I'll notice that I have 2 hydrogens from the zinc hydroxide, 2 hydrogens from the nitric acid, whereas on the right side, I only have 2 hydrogens total, and that's from water. I can balance those fairly easily simply by adding a coefficient of 2 in front of water. And that will now get me a case where my hydrogens are now balanced at 4. In the process of doing this, I will notice that my oxygens also became balanced. This will not always be the case, but in some cases, in the process of balancing the other elements that appear in the fewer number of formulas, you end up balancing the remaining elements even before you get to addressing them. And so this is really a straightforward example of how you would balance an ionic equation. And before we leave this section on balancing chemical equations, we need to note 2 more things that show up commonly in chemical reactions. And those are the states, or the state symbols for the compounds. These are symbols that indicate the actual physical state of the compound, whether it's a gas or a liquid or a solid. We would use G, L, or S in parentheses after the chemical formula. Or there is another state. This is known as aqueous. This is simply when the compound is dissolved in water. So if we were talking about a reaction involving table salt, sodium chloride in water, in that case, it's not a solid anymore because it's dissolved in water. And so we would refer to it as aqueous and put the symbol AQ in parentheses after the formula. These will commonly appear in chemical reactions and are useful for telling you what state you're starting in. So a couple examples I'll show in a moment. However, there's also one more case, and this is for reaction conditions. And these are things that we would put above or below the reaction arrow. There sometimes can be other cases as well, but if we have to heat a reaction in order for it to transform the starting materials into the products, we can write heat, or we can put the Greek symbol delta above or below the arrow. Also HV, which should really be H nu here, but we often write it as HV. This is simply a symbol for light. So if we need to shine light on a reaction in order for it to go, we will sometimes put that as a reaction condition above or below the reaction arrow. A few examples here, one that we've done before, simply putting in the phase symbols. Now you can see oxygen is a gas, CO2 and water that are generated in this process are gases. Another case here in ionic reaction with these cases, this would be in aqueous solution. So this is a case where we would be doing this reaction in water, and so we would write aqueous after the chemical formulas. With the exception of water here, Water cannot be dissolved in water. We don't talk about it in that way, and so it's simply a liquid in this case. Case where we would involve heat and list it explicitly above or below the reaction arrow. Here, the combustion of hydrogen and oxygen to form water gas. This is certainly a reaction that involves heat, and so we write the delta symbol above the arrow.